Hello, Professor. Good afternoon.
Hello? We are waiting for other students to join us. So please, let's wait a bit.
Hello. Okay. Yes, class starts at in 10 minutes.
I think so, yes.
Okay.
Okay, we'll wait a little bit further for the students to join us. Sorry for late notice. So this lecture and the following on one today and the lectures tomorrow will be online, and then we'll see. So it is quite possible that all of them will be online.
Okay, that
So
looks
please
good.
stay tuned.
For myself,
Sorry,
online is more better.
couldn't quite hear you. Could you please repeat your point?
I said for myself, I like online more.
Okay, so for most students, you say online is better, right?
For myself personally,
Ah, so most students would like face-to-face.
I do not know. I do not know.
Well, let's see. Let's see. Actually, I don't think there is a big difference. We'll see. For the moment, we're starting online. Okay, greetings. So there are four of us. Let's wait a little bit more and we'll start. Okay, great. Six of us, so we're starting soon. Wonderful. Okay, great. Can you hear me?
Yes.
Yes,
All
good
fine?
afternoon,
Okay.
Professor. Yes.
Good afternoon. Thank you. Thank you for coming. So for the moment, to begin with, at least today and tomorrow, we'll have our lectures online, and then we'll see. Actually, it may be that we'll continue online. We'll really see what the best way of doing that. So let us do some preliminary discussion. So first of all, I have created, no, not I, actually Arseny, one of our students, had created a Telegram group for us, formally verified operating systems, and I think all of us are in this group. So please stay tuned. All announcements will be there rather than by email, because I realize that actually Telegram is much more convenient than using email to that end. It is with our mobile devices and with everyone. All right. So then our lectures will be recorded and published on YouTube. Links will be both actually in Moodle, links to our lectures, uh, if online, but it may even be that if we do an offline lecture, we'll still record it and publish it on YouTube. And also, if online, I'm going to use an interactive whiteboard. So I have a pen. Uh, so our whiteboard images will be published in our Telegram channel as well, so you can review all our writings during the lectures. Okay. Now,
I'm sorry, sir.
yeah,
Can I ask question?
yes, of course, please feel free.
Uh, I believe that we are three online students in this course. So will be there a mixed format lectures?
Um, it depends. So it looks to me that online is more convenient, but what do you think? Mixed, you mean offline with recording and online broadcasting, or how?
I mean that if you will do some offline lectures, and would you make an online
Oh,
broadcast?
yes, definitely, yes. Both actually broadcast and recording. Um,
Yeah, thank you.
but to
Thank you.
begin with, we will do it online, and I believe that it is probably more convenient to do online. Only if we encounter some prohibitive difficulties which do not allow us to do it online well, then we'll switch to a mixed, to a hybrid format online with recording. So, okay, now. Um, you are all first and second year MSc students from Innopolis, right?
Yes.
Because it may very well be
Yes.
that students from other universities may also join us at some point. Maybe tomorrow, from tomorrow on, we'll see. Uh, Let me explain what we want to do actually in this course. Maybe it will be a little bit more broad than just formally verified operating systems. Maybe I will be talking about formally verified and real-time operating systems, because actually these two topics are very close to each other. Um, First of all, I would like to ask you, your first degree, presumably it was kind of BS in computer science or something like that, right? For all of you.
Not
Not really.
Not really.
My
Okay.
Yeah, my first degree is civil engineering, and here I'm a robotics student.
Oh, perfect. So that's definitely a very good course for you. Great. Okay. Any other backgrounds, please let me know, because it will help me with just planning, adjusting, customizing our course.
Yes, sir.
Actually,
I have a bachelor degree in mechanical engineering, designing and production engineer.
Great. Okay, fine.
Actually, sir, I have a bachelor degree in electronics engineering.
Perfect. Okay, okay.
And me, computer engineering.
And computer engineering. So actually, many of you have a background related to either hardware or mechanics or digital signal processing, right? And you are doing an MSc in software engineering. Okay, perfect.
My
Now,
case is a little different compared
yeah,
to others. My bachelor's degree is, I have two bachelor's degree in English literature and also computer science, IT.
okay,
But I have fair familiarity with electronics, and I worked in the industry for about a long time, maybe 10
perfect,
years.
perfect. Yes, yes. So that's all great. So I think your backgrounds are entirely suitable and perfectly suitable for this course. I will just make a little bit more, I would say, bridges between your areas of prior specialization to what we are going to discuss now. Okay, then some of you may or some of you may not uh, have had a formal course in operating systems in your bachelor degree. So who did? Could you please let me know?
What do you mean by formal?
That you had a module, a subject in your BS, which was called operating systems.
Yes, I did.
Okay, you did. Any others? Yes. Minus plus plus. Okay. Minus. I see the voting. Please. Minus. That's almost all. Okay. Plus, but as a free listener. Okay. Never mind. So even better. In that case, we'll structure our program in the following way. So first of all, there will be some general introduction into operating systems. We'll start with that right now today. And following on will be a part on formally verified and real-time operating systems. For those who came from mechanical engineering and robotics background, for example, real-time properties of the operating systems are very, 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 very important. Because obviously, if you have a system which performs some kind of real-time control, then the system must be bound by some temporal guarantees. And if the system fails to deliver its control services within a specified period of time, then anything can happen. For example, technological failure, if, for example, a robot is not properly controlled. We'll come to that point later. So let us, you see, in our course, there are lectures and practical sessions, but I will be doing both of them. We'll be interleaving them freely. So, for example, if we need more time for a lecture, then we'll do a lecture. If we need more time for a practical session, we will do a practical session, something like that. So altogether, there will be 20 lectures and practical sessions, as far as I understand, in the remaining part of the term. Okay, so let me start our whiteboard. Please feel free to ask any questions if anything is unclear. It may very well be. Don't be shy. It's perfectly okay to ask. All right. So I'm switching to my whiteboard. If I find it, just a second. Here we are. So the first question is, however simple it looks like, but what is the operating system in general? And I will...
Maybe it is a program.
Yeah, please.
Do you want us to answer? Or...
Yes, please provide the answers, yes.
It's a program that plays a role between the user and the computer hardware.
Okay. Intermediary. Oh, sorry. Intermediary. Between the user and the hardware. Okay. Any other ideas? In general, I would agree, of course, with that. Yes. Anything else?
Low-level software which controls and make work together different parts of hardware. Operating system, not just of the computer, but of a spacecraft or whatever.
To control the hardware, right?
To control and connect different parts of hardware.
Okay.
I can say like this, that the operating system is a software that normally takes control of the firmwares, that they may use different languages or different specifications, and it needs to make a translation between them and provide an interface to the software, the high-level software that normally a user or another application uses.
Generally, let me say, if I slightly rephrase what you say it is a hierarchy of interfaces, of layers and interfaces, which is definitely correct as well. And so on. So there is no, I would say, one and for all definition of the operating system, but indeed, in general, by the operating system, we mean some kind of software which is, first of all, normally continuously running, that's important, continuously running on the hardware. An application program can be started and terminated. The operating system is continuously running. Which helps us to organize the computational process in a way which is convenient for the user, or I would say convenient for the application level. Not all operating systems are user-facing. For the vast majority of them, which we know, it is indeed an interface between the user and the hardware. But there are many operating systems, for example, found in embedded devices, and now I think it's going to be really myriads of them, because we are facing the arrival of the Internet of Things, with lots of consumer devices being controlled by their own computing modules, comprising hardware and operating system, some kind of application. In that case, the operating system may or may not be directly interfacing the user, but it is definitely interfacing the hardware. And actually, we'll see when we see the hierarchy of layers, and the hierarchy of layers, as one of you had pointed out, is a very important indeed feature characteristic of an operating system. That some of them may belong to really an operating system, some of them may belong to a firmware, as we pointed out, some of them may be somewhere in the operating system and the application programs. So we'll draw up typical hierarchies and see how it actually works. There are some synonyms to the term operating system. So apart from, okay, it is an operating system, what else, which are the terms we could use? Maybe not exactly equivalent to the operating system, but very close to that. What do you think? Which terms have you heard?
From robotics, it's controller or just control.
But a controller can also include the hardware. So we typically say hardware controller. So it might be, but, well, close, but not exactly. So first of all, we have heard the term kernel. All right? The kernel is a notion which is a little bit more narrow than the operating system. And the difference between the two, we will see when we study just a particular example. We'll consider the Linux operating system and how it works. And then the difference between the operating system and the kernel will become more clear. But to a large extent, you can say that, yes, the kernel is a major part of operating system to such an extent that sometimes we can say that the notions of kernel and operating system are equivalent. In the real-time and embedded systems world, also apart from this, when you said controller, yes, it is just said slightly differently. We call it not a controller, but executive. Not executable, a big difference. Executable is a file which can run, which contains machine commands, and which can run on top of an operating system. So an operating system loads this file into the memory of the computer and gets the corresponding code running. So that's executable. Executive is typically a term, you may or may not have heard it, for a real-time or embedded kernel. So these three terms, mostly. A kernel itself may have a very interesting structure. So it may or may not be, let's say, monolithic. And in that case, actually, it is a good point to discuss the structure of the kernel, what it consists of, the hierarchical, as we say, hierarchical levels of the kernel organization, and so on and so on. Okay, so now a poll: which operating systems do you run at home? I will provide my answer as well. Well, which world we? Okay, Ubuntu, Linux. Okay, great. Windows 10. Oh. Okay. My own entry. The notebook which I use now for this lecture runs Fedora 33 Linux. Yes?
I guess the best of them, most stable one is Red Hat.
It is good. You see, what is really good about Red Hat? Red Hat, Fedora is Red Hat indeed. Is that they combine a really good stability with periodic releases. So Fedora is released every 6 months. The first release of Fedora line came in November 2003, and since then they missed the slot for semi-annual delivery only twice. So if not for those misses, we would now be in Fedora 35, whereas in reality we are in 33 only. But you know, for 18 years of development, this is not bad at all. Another distribution of Linux which I like very much and which I use quite a lot is Arch Linux. You may have heard about it, Arch Linux. But there are myriads of Linux distributions currently. So you see, we are in basically in Linux and some of your Microsoft Windows world. For me, I haven't been using Windows for many years now. There was simply no need, and the open source Linux perfectly nowadays is perfectly sufficient for all tasks we can think of. By the way, although we are going to talk about formally verified operating systems, would you like to have at least some material in our course to be dedicated to advanced Linux features? I think it might be a good idea. What do you think?
Like what? Like OEM drivers or something like that?
A quick, yes, sure. I received. Let me do the following poll. So, okay, Linux is good. Now, how do you use Linux? Have any one of you ever compiled a Linux kernel by yourself? Anyone? No? You say not yet? Not yet? No. Off. I think compiling a Linux kernel is an absolutely excellent exercise, which we should do. There is a reason why. I will explain to you. Recently, I have been involved into activity and still involved a little bit into this activity which is called high frequency algorithmic trading. What does it mean? You probably know what it means, right? It means that we connect to a certain exchange, ideally financial exchange. Nowadays, very often this could be a crypto exchange, but not necessarily. And from this exchange, we receive market data. We can place orders to buy or sell financial securities to this exchange. And obviously, when we placed an order, then we would like to know what happened with that order. So we would receive order status for the orders we have placed. A component which does all this is called algo trading platform. I would even, instead of just high frequency, I would also sometimes say ultra high frequency. So we have our algo trading UHFT, our ultra high frequency trading platform. What is this platform? The platform has connectors which really performs connections to the exchange, send messages, receive messages, parse the messages received, update the state, and so on. And also, there is a so-called precisely algo trading strategy. This strategy really makes business-like decisions. So, for example, we receive a market data which tells us that the price falls for a particular instrument. What should we do? Buy or not, for example. And if a decision is, according to the strategy, to buy, then the strategy sends an order to buy. And what we would like to do is, first of all, to achieve the minimum communication latency, if it is really high frequency algo trading. And this minimum communication latency is achieved by collocating our algo trading platform in the maximum proximity, maximum close proximity to the exchange. This is typically done by collocation. You may or may not be able to achieve this collocation. So, for example, for most old financial exchanges, so-called fiat exchanges, you can do that, although it costs quite a lot. For crypto exchanges, which are hidden somewhere in the internet, you may or may not be able to find a data center which is very close to the actual location of the exchange and provide the collocation. But suppose that we did our best and we really minimized the communication latency here. But we would also like to minimize the response latency. What does it mean to minimize the response latency? I can give you an example. So a market data in a collocated environment is typically sent not even by, what do you think, which protocols could be used here? You definitely studied some internet protocols for information exchange between the exchange, financial exchange, and our trading strategy. So which protocol should I put here?
Maybe we can use socket.
Sockets is not a protocol. Socket is the API, which is present in Linux and other Unix systems. You're absolutely right. So actually, all these communications are performed, and we can say they are performed by wire socket API. I put it here.
Which protocol you mean? Which layer? Because each layer has their own protocol, and we should use
Yes, but in general,
typically
what do you think?
TCP.
Yes. So typically, for orders, for placing orders and receiving order status, we use TCP and some extensions on top of TCP. Which extension? There is a special FIX protocol, which is called Financial Information Exchange. And sometimes, very often nowadays, there is that's by the way unfortunate. That's a bad idea. There is a WebSocket and HTTPS used to that point. WebSocket and HTTPS for crypto exchanges, FIX for classical old-style fiat exchanges. So all these are TCP based. For market data, the situation is slightly different. You may also use TCP-based protocols such as FIX, WebSocket, and HTTPS, but sometimes if you have a really good collocated environment, then market data is delivered by multicast UDP instead of TCP. You probably remember the differences between UDP and TCP, right?
Yes.
Okay, in your day-to-day life, do you experience UDP with any of applications? So for example, you're on whatever application and that application performs network communications by UDP. Can you name any?
Zoom.
Maybe, I don't know. Maybe, maybe not. I would say that IPTV quite often is implemented on top of UDP, your digital television services. What are the main advantages of UDP over TCP? The main advantage is lower overhead and as a result, simply higher throughput and lower latency. Why? Because UDP is datagram oriented. So first of all, when your message comes into your application, it is much easier, first of all, to find the boundaries of your message. Can you tell me, please, so did you do any TCP/IP programming? Not necessarily including UDP, but just TCP/IP programming in your student projects, in your commercial maybe projects, anywhere? Probably you did. Again, let's do a brief walk. Okay. Oh, by the way, yes, Anthony says, yes, versions of RPC and of course DNS, which is a very good example, are implemented on top of UDP. You are absolutely right. DNS is the naming service on the internet, which allows you to obtain an IP address of a host by providing a symbolic name. So TCP/IP programming you did not, or you did very little, and again, we should probably in this course cover that little bit at least, because TCP/IP programming, which means actually using the socket API as we currently normally use it. Socket API is the standard API for TCP/IP communications. It is also a major part of any operating system, And that needs to be, actually, it is a very good example of how important operating system services work. And that's why I think it is a very, very, very good idea. So, okay, perfect. We will little bit broaden the scope of our course, and we'll talk about important properties of the operating systems in a more general context. Fine. Now, so without going into the detail of TCP and UDP, TCP communication really behaves like, appears to you like a stream of bytes. So you receive a stream of bytes from a TCP socket, very much like, for example, you would on each and every read receive a stream of bytes when reading a file. And the question is, typically, the communications which the exchange or any other counterparty sends to you, communications are structured. So there are message boundaries. When you receive a TCP communication, then these message boundaries are not marked in any way, which means that you really need to scan the input you have received and to determine those boundaries by yourself. So it may very well be that, for example, you received some bytes, but not to the end of the message. And in that case, there is no way of how you can process those bytes, because the head is present, the tail is not, and you need to wait and read more bytes when they become available, when the sender actually sends them and they get delivered, before you can really get the message end, and therefore frame out the message, and you would be able to process it. Whereas the following on bytes, which form a partial yet incomplete message, need to be retained somewhere in a buffer, and you would be able to use them when a new complete message is received afterwards. Something like that. Whereas for UDP, you are free from that trouble. For UDP, you receive messages which are already by the operating system, actually by the protocol, by the network protocol, and by the operating system which implement this protocol, are already split into logical messages. So you receive an entire message and nothing apart from it. When you do a second receive, you receive a next message, and so on. So you are not concerned in this case with finding logical message ends and beginnings. You can rely upon the UDP protocol to do that for you. The problem is that UDP, unlike TCP, is so-called unreliable. Those messages may simply be lost, or even if not lost, they can come out of order. So what we say, TCP, stream-oriented, which means message boundaries must be found at the application level. Reliable in the sense that data are not lost. We would say connection-oriented rather than UDP, which does not use the notion of connection. Don't bother that much about the notion what is connection-oriented. We may see it later. UDP, and I would say a relatively high overhead. This high overhead comes from these stream like features and reliability. Whereas UDP is message-oriented, so-called unreliable. Messages can get lost or order mixed up. Message 1 is sent before message 2, but message 2 arrives before 1. That's possible with UDP. On the other hand, yes, UDP, it may have a notion of a connection, but it means something completely different than that for TCP. So we would say it is connectionless. And low overhead. Low overhead is extremely important. So if you are in the very, very proximity of the exchange, so for example, your computer, your host running your UHFT platform is really connected to the same switch as the computer on which the exchange matching engine is running, then we can't say that UDP is unreliable. UDP becomes unreliable only when UDP messages traverse many intermediate routers. Then indeed anything can happen. So for example, the router goes out of order and the corresponding message is lost. Or for whatever reason, although that's quite unlikely, even the order of the messages gets altered, which is quite unlikely actually. Nevertheless, the protocol formally does not guarantee that the messages come in the same order. But if there is just a very single, let's say, connection, hardware connection between the source of your data and the data consumer, then UDP is reliable. UDP can be fully relied upon. Or if you are really concerned about potential message disappearing, you can, for example, instead of getting one UDP stream, you can get two UDP streams, and in this case, the probability of a double loss becomes absolutely infinitesimal. So the question is, when we talk about this low latency system, what do you think is a typical reaction standard? So an exchange sent us an update. So for example, a price update for a particular financial instrument, either BTC USD or USD ruble or whatever. Our strategy must receive this data without the communication time. So from the point of the data entering our network card to the point when we react upon that and possibly send an order, let's say, to buy USD in this case. So what do you think is the loop, the reaction loop, which is the latency of this reaction loop in high frequency algo trading platform? So it is measured in what? In seconds, milliseconds, microseconds, nanoseconds, and how long do you think would typically it be?
I'm sorry, Professor, will there be acknowledgements between the two stations?
If UDP, then not. So UDP comes without any acknowledgement. So a UDP datagram is just sent from the exchange to you, and we start our timer at the point when we have received it. We do not send any acknowledgement. we just read the data which arrived in this UDP datagram to us. The data, for example, indicate that, put it very simply, USD ruble price was 75.01 and now it is 74.99. And our trading strategy says, oh, 74.99 is cheap. 75.01 is expensive, but 74.99 is cheap. So let's buy it now. And for this data to be read, parsed, processed by the strategy, decision made by the strategy. Okay, in this case, it is a simple if, but it could be much more complex than that. Okay, we see the price, we decide to buy, something like that. Then prepare a message to be sent now by TCP to the exchange. Buy message. And preparing this message, putting this message through the socket, and up to the point when really the corresponding bytes leave your network card on the wire. So this from the wire receive of UDP to wire send of TCP. What do you think a typical response time is?
It depends on the processing unit speed.
On our processing
with
unit. That's our host.
Yeah.
That's our host. So we run this UHFT platform, and this UHFT platform obviously runs on top of some operating system. UHFT platform is application level software. It runs on top of an operating system. So altogether, receiving the data, processing the data, preparing output, and putting the output through the socket. How long do you think it may take, and what would be a normal response time in the modern competitive environment? Let's calculate together. So first of all, could it be in, let's say, nanoseconds? The answer is probably not, because the typical CPU speed, let's just get things into proportion. The typical CPU speed is, let's say, we run at 4 gigahertz. What does it mean? It means that this is a frequency of your CPU making some operations. For each tick of this frequency, the CPU may perform just one machine instruction, or maybe sometimes even it would require, it would be able to do several machine instructions at once. This might be possible, or it may be possible other way around, that a single instruction would require multiple ticks. So we really don't know. There are two processor, not architectures, but I would say very large families of CPUs, which are called CISC and RISC. You know this term, what CISC and RISC means, probably. First of all, what is RISC? A reduced instruction set computer. Actually, not computer, but CPU. But the term sticks. We call it RISC. And CISC is conventional. Not conventional means not reduced. Instruction set computer. Okay, The computer architecture which we use in our PCs and notebooks every day, how is it called? The architecture. Not the model of your CPU, but the architecture. For example, on the computer which I am currently using just for this lecture, what kind of processor is?
The conventional computer, it's CISC,
Yes.
I suppose.
It is true. So first of all, the processor architecture is obviously called Intel. Well, not necessarily on Intel. The architecture is called x86-64. And that belongs to CISC, which is a successor of Intel 32-bit architecture, which was called actually Intel IA32, and all those classical processors like Intel 386, 486, 586, Pentium, and so on, they belong to this 32-bit architecture, but now it is 64-bit, and it is called x86-64. Why it is not entirely Intel is because this architecture was originally invented by AMD, Intel's arch-rival. Yes? You agree with that?
Yes.
It originally came from AMD, and only then it was supported, taken, and advanced by Intel. So these are examples of CISC. Okay, in your just closest neighborhood, maybe in a radius of 1 meter from you now, where is RISC?
In mobile phones and tablets?
In mobile phones, absolutely. So which processor, again, architectures are most commonly used in mobile phones?
64.
First of all, it is ARM.
ARM 64, yes.
Yes, ARM 64, yes. And then many implementations of this ARM 64, which is RISC. Okay. Can you name possibly some other? These are by far the most widely used representatives of both architectures, actually, CISC and RISC.
Apple Silicon, Snapdragon.
The new Apple CPU is going to be RISC as well, yes. Actually, the story is, when modern microprocessors came into existence, and that was which was, by the way, the first, it is still in use actually, only by embedded systems. The first 32-bit, maybe not the very first, but the first very commonly used 32-bit processor. And when did it come? Interestingly enough, very long time ago. In 1978, there was a Motorola 68K, and it was already 32-bit, which is impossible to imagine nowadays. In 1981, Intel 8086 came, but that was only 16-bit. So it is not really a modern CPU. In 1986, though, Intel 386 came, which was already 32-bit. But Motorola did it 8 years prior to Intel. And yet eventually the 68 family 68K family died out, whereas Intel became completely prevalent. So these were all examples of CISC. The RISC architecture came in 1980s, and there are many representatives of this. So first of all, you have, of course, heard about SunSpark. Now there is no Sun, but the Spark architecture still exists, and it is owned by Oracle, as you probably know. There are, at the moment, no real advantages of using Spark compared to, let's say, x86 64. There is also a 64-bit version of Spark later. But there are solutions, for example, very highly dependable server-side solutions which are on Spark, and simply from the, I would say, maintainability point of view, it is very difficult to get them switched back to Intel. So Spark still exists. Another one was MIPS. MIPS is still very widely used, actually. Not for consumer computers, but for embedded devices. For embedded devices, MIPS is a very widely used family of microprocessors, and so on. So many of them are now defunct, but some of them do exist, and these are risks. Of course, there was an HPPA architecture from HP, the so-called Hewlett-Packard Precision Architecture, HPPA. Alpha from DEC doesn't exist anymore. The first real 64-bit one. Okay, let's do a short break and then we continue from that point on. Okay, so getting back to our point. The RISC architecture was really invented for the purpose of simplifying the instruction set of computers, because even the Intel instruction set at that time was very much complicated. For example, machine instructions or machine commands have all been of different size. So for the processor, even fetching them into memory, fetching them from memory was a not so obvious and easy task to do, which had a performance impact, a performance overhead. So RISC precisely was designed from the point of view of all instructions being of the same size, and one tick of the CPU speed being exactly one instruction. So in that case, for example, if it were a RISC system, then 4 gigahertz system would exactly mean 4 billion instructions per second. With our CISC system, we are not completely sure about this. So it may be less than 4 billion instructions per second. It could be more than 4 billion instructions per second. But suppose that, just for the sake of the argument, we don't know, but we'll approximately say this means 4 times 4 10 to 9 instructions per second. With RISC, we would be sure about that. With CISC, we don't really know, but suppose that. If, in that case, if the time, let me, response time tau is, suppose that it is 1 nanosecond. Suppose that it is 1 nanosecond. This would mean that within 1 nanosecond, nanosecond is 10 to minus 9, right? If we run at, for example, for the sake of the argument, suppose that we run only one core. So it's not a multi-core system in which we parallelize our processing. Not everything can be very easily parallelized. So if we need to just read the datagram and process it, then it may very well be that sequential processing would provide lower overhead than parallelization. So if it is 1 nanosecond and we are running at this CPU speed, then how many instructions can we execute within 1 nanosecond?
Four instructions.
Only 4 instructions. Of course, 4 instructions are completely insufficient to do any kind of logic, because you need, first of all, to receive this datagram from memory, to parse the data which are contained there, to call the strategy, to let the strategy decide what to do with this data, to prepare the output message, to go through the operating system socket and output that message. So as you can see, 4 instructions are by far not sufficient. So it could not be a nanosecond range. We would like to, but it is completely impossible to have, with the present day technology, it is completely impossible to have a nanosecond response time. Now, if tau is about 1 microsecond, micro prefix is mu. Mu sec means a microsecond. Okay? Which is 10 to minus 6 seconds. Then it is already 4K instructions. In 4K instructions, you can already do something. I would say still probably not extremely much, but you can do some very simple operations. So I would tell you that for typical UHFT, ultra high frequency trading platform, the response time would be not 1, but we would say 5 microseconds, which would translate into 20K instructions. 20K instructions are already, or something like that, are already sufficient to do some kind of meaningful, first of all, operating system processing, and maybe some meaningful business logic. Okay? So now, with those 20K instructions, most of those instructions would occur not within your application level. Within your application level, I don't know precisely how much, but again, first the data comes into your network card, and then the data needs to be read into the computer main memory. And what is the data? The data as you originally received. What kind of data do you receive from the network? You receive an Ethernet frame. Within this Ethernet frame, there is an IP datagram. IP. Within the IP datagram, there is a UDP datagram. And it is the UDP datagram which really contains your useful payload. So when the data comes in, not only it needs to be transferred from the your network card to the main memory, but all those header and footer fields from the Ethernet frame, from IP datagram, they need to be stripped out, and then the useful data eventually comes through the socket into your application, which is your UHFT platform. And when you send the message back, then it is a completely opposite story. You take your payload. The payload is packed in this case into not a UDP, but a TCP message, then into an IP one, then again into an Ethernet frame, and sent out back by the wire. So my point is, in this kind of activity, and remember that we only have 5 microseconds to perform this activity, out of them, a significant part of activities is done not by you, not by your application program. In your application program, you typically do not parse Ethernet frames, IP datagrams, UDP datagrams, and so on. What you do, you simply read the data from a socket, right? That's what you do. And then you put the data back into the socket. And the rest is precisely to be done by the operating system. So here, it is a great example of how the operating system, by implementing a certain type of functionality, allows you to structure your computational process in a way which is convenient to you. It abstracts you from details such as how the network card works, how this Ethernet IP, UDP, TCP frames are to be constructed. You are not to bother with anything of that. You delegate this activity, these services, to the operating system, which does it for you. So out of these 5 microseconds, I would say probably something like that. 3 microseconds are spent inside the kernel. Plus, yes, 2 microseconds, for example, are spent within your application. When you optimize your solution, not only would you optimize your application, how would you optimize your application? You would optimize your application by using optimal data structures, by compiling your code with the maximum optimization level. You remember in typical C++ compiler, for example, there are those famous flags -02, -03. which allow you to compile the code with the maximum degree of optimization, right? Then you can optimize this part. So basically, if you do not optimize it, then it's going to be much more than 2 microseconds. 2 microseconds with full optimization. Okay. But the question is, what happens here in the kernel? Does it mean that because this is the kernel, it is completely beyond your control? And if beyond your control, you are not able to optimize the performance of the kernel? Of course, that's not true. If your operating system is Windows, then it is indeed the case, all bets are off. The operating system kernel is completely beyond your control. You cannot do anything with it. Once a kernel call is done, so the control is passed from your application level software to the kernel, then you are completely at the mercy of what the kernel would do for you. And it may be significantly suboptimal. Nevertheless, you have absolutely no way of what to do with that. But with Linux, it is not the case. With Linux, you do have control over your kernel. So I would say optimize and recompile your kernel. And the difference in timing, in temporal properties of a fully optimized and not fully optimized, let's say, stock kernel. The stock kernel is the one which comes with your operating system. So for example, you install Ubuntu or you install Fedora, and there is a pre-installed kernel which comes with your operating system, which is called stock kernel. The difference in latency between the situations when you use a stock kernel and you use your own kernel can be maybe not so huge from your point of view, let's say 10 microseconds, but it is really huge in this case. Either you spend in the kernel only 3 microseconds, or you spend 13 microseconds in the kernel, which would mean that the overall response time is either 5 microseconds or 15 microseconds, right? So it is a 3-time difference. And in the world of UHFT, each and every microsecond, maybe sub-microsecond even, it matters. You get a competitive business advantage by reducing as far as possible the latency of your algo trading platforms. For example, really there is a price drop in the market. It is this 74.99 now. A UDP broadcast message is sent to all trading platforms, all clients connected to the exchange. And suppose that it is a broadcast which comes through the same switch, and that's why it reaches all clients simultaneously at the same time. Then the competitive advantage belongs to the client, which reacts faster. And in that case, the difference of not just 10, but maybe even 1 microsecond between the fastest one and not the fastest client would mean that the fastest one would really be able to take this trade, to execute this trade at the lowest price. Whereas when other people come, then they would be left. They could still buy dollars if they want, but not at 74.99, but only at 75.01 as a result. The difference is maybe not so significant for us, but for high-frequency algo trading companies, which make profit precisely by exercising this very, very, very high-speed operations of, let's say, buy low, sell high, the difference may be very much significant. So to achieve the lowest possible latency in this situation is of paramount importance. And one of the ways of doing that is precisely, first of all, to understand your Linux kernel, and secondly, to be able to recompile your Linux kernel in order to structure it and to optimize it precisely to satisfy your requirements. Okay, another example. Another example is an embedded system. Let's say Internet of Things. And suppose that we're still using Linux with this embedded system, which is quite a normal situation nowadays. So using Linux at both actually top-level world supercomputers and in embedded systems is a completely normal practice. But in this case, you are concerned not only about the performance, the speed of your kernel. The speed would not be that much huge because in the Internet of Things, your processing power is limited. So it's definitely not a 4 gigahertz CPU in this case. It could be probably some 1 gigahertz or maybe just under 1 gigahertz processor with embedded memory still running Linux. Your major concern is the memory footprint.
I'm sorry, Professor. Can you provide an example of IoT embedded system? This is the first time I hear of this.
Oh, okay. IoT embedded system is in my kitchen. It is in the smart fridge, which has a control unit. First of all, it provides very smart control of the temperature inside the fridge. And also it has a communication module, which in theory, I didn't do it yet, allows an external wireless connection to this module so that you can control your fridge from outside.
Thank you.
The maker is Faotsug. But I didn't use it with external communications yet. I only know that it is an extremely complex control system, which if you extract this board, it really looks like a motherboard of a notebook. It is about of that size. And, you know, unfortunately, it even costs about that price as well. So once it was at some point killed by a power surge, I nearly had a heart attack. So still, such a device has a relatively low memory. We're not talking about large, let's say, gigabytes of memory in this case. Probably has under, I'm not sure precisely that one, probably has under 1 gigabyte, maybe hundreds of M, I'm not completely sure. You need to make sure that your operating system fits within low memory. can you, for example, configure Windows kernel to such an extent that it would fit in an embedded device? In theory, yes. There was a claim by Microsoft that Windows 10 is not just Windows 10 for desktop computers, that it is the whole line of operating systems which can be used for any platforms, from embedded Internet of Things devices to smartphones, to desktop computers, desktop and notebook computers, to supercomputers and servers. But in fact, Windows system scales very badly. When we say the system is scalable, and that's, by the way, very important thing to notice. When we say a solution is scalable, we normally mean that the solution is scalable up, right? So that, for example, it can, with the simplest configuration, perform a certain workload, but we can install, let's say, extra CPUs, maybe run it in distributed environment on multiple computers and so on, and then with n times hardware resources added, the performance would be scaling up almost proportionally n, all right? That's what we mean by scalability. But by scalability, we should always remember there is another side of it, which means scaling down. So if your system really needs to run on a very limited hardware resource, another example I can tell you about is, when was it? 7 years back, almost 7 years back, I was designing a control system for, you know, for what? In Moscow, there is a very famous Yermolova theater. And I was designing a control system for lights, for the scene lights in this theater, which is, by the way, a very interesting and challenging and not trivial exercise, because most of your controllers are running some kind of embedded Linux. They're very low-end 32-bit processors, and there are even some running in 62-bit environment. And also, as 32-bit old-style Intel 386 processors, they didn't have a floating point unit. So you couldn't perform any floating point computations. Whereas lights control was precisely an application of some kind of nonlinear function which maps voltage which you provide to the lamps to the intensity of the light. And it could be some kind of non-linear relationship between them. So the voltage is obviously limited by, let's say, the maximum of 220, but it could be less than that. And then in some kind of non-linear manner, you receive a certain intensity of light when you move your voltage regulator, when just the light engineer in the theater throughout the performance moves the controls, and by changing the voltage or some temporal parameters, they would change the light intensity. So that was all controlled through a microprocessor system, and this type of control functions had to be devised without floating point arithmetic. And yet it was possible to do that by providing some kind of table-driven solutions. And it was still running on top of Linux, only a very minimum one, a stripped down, just, you know, a very, very, I would say, minimalistic version of embedded Linux. So that's why Linux is nowadays, for Windows, you wouldn't be able to do that. You really had to customize and optimize the Linux kernel for this type of application. So it has the full range of devices. Now, Internet of Things are the embedded to desktop notebooks, to servers, to supercomputer architectures. If we consider this as a 0.0, let's say our conventional desktop notebook, then being able to run Linux efficiently on large servers and supercomputer clusters is scaling up, obviously. And running it on Internet of Things and embedded is scaling down. Linux is not the only free and open source operating system, as you probably know. Apart from Linux, what are other, I would say, maybe common, maybe not so common, open source operating systems you know? Okay. Have you heard about the BSD family? So, for example, FreeBSD, OpenBSD, NetBSD, I don't know, Dragonfly BSD, and maybe some others. Have you heard about them? Not really. The BSD family is a very interesting one. They, in fact, predate Linux. So basically the story is, if we do not go into ancient times, then the modern computing emerged around 1969, 1970, with the advent of, first of all, Unix operating system and the C language. They are very closely related to each other because C was used for implementation of a very large part of the first Unix kernel. This is the very, very first days of Unix, the work of, you remember, Kernighan, Ritchie, if I spell his name correctly, Janson, all those pioneers of Unix. And that was at AT&T, Bell Laboratories. Then what happened is that AT&T made this first Unix operating system open source and almost free. Almost free means that you would be able to receive it for free, run it for free, but still you couldn't distribute it for free. In order to get a license, although a free license, yes, with the source code, you had to ask AT&T for licensing. And then at some point, so that continued to be AT&T Unix at some point, which was probably end of 1970s or something, AT&T started charging fees for Unix licenses. The operating system became more and more popular, so they decided that the time was high to stop giving it out for free and fully commercialize sales of Unix licenses. And at that time, because it was already widely used, especially in academic community, the University of California at Berkeley decided not to pay for AT&T licenses, but to completely re-implement Unix. And this complete re-implementation of Unix is precisely called BSD. BSD stands for Berkeley System Distribution. This is a Berkeley Unix. And in your software world, you probably have seen many types of licenses associated even with free, ostensibly free and open source software. So for example, GPL, GNU Public License, BSD license, Apache Creative License. Have you seen that? Have you seen those? Of them, BSD is very, very, very liberal. So you are really free to take the source code of whatever BSD licensed software is, in particular the Berkeley system distribution, and modify it as you see fit, even include it into commercial products, even sell the derivatives of that without any restrictions. GNU public license is much more restrictive. If you acquire free software under GNU public license, you are not allowed to make non-open source derivative works out of it. So if you modify it, then the modification needs to be free as well. Free, at least in the sense that the client would receive full open source of it. You may charge fees for that the license doesn't prohibit, but the open source must be released. And those, first of all, BSD licenses and BSD family of Unix systems are very, 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 very popular even today. Where the original AT&T, through many evolutions, eventually found its way into, for example, Sun Solaris, into Solaris operating systems, which has nearly been discontinued after Sun was acquired by Oracle in 2011. Whereas BSD and especially those modern versions of BSD, like FreeBSD, OpenBSD, and so on, are very much popular even today. And the third line is indeed Linux, which is neither BSD nor AT&T, like also called System 5. There is another term, type of Unix. So all of them are Unixes. Linux, BSD, Solaris, which is System 5, which has its origin in AT&T, although probably not a single line of code remains nowadays in Solaris, which was previously, written for 50 years ago for AT&T system. But all of them are Unixes, or as we call it in singular, it is Unix. In plural, it is Unixes. Nowadays, BSD is still a great system. You can run it on the server side. You can run it as a desktop. It is a good thing. It is relatively simple. It is just very robust. It is a bit conservative to change, but performance-wise, especially when we're talking about high performance. High performance, low latency systems, they are primarily not based on BSD nowadays, and we base them on Linux typically. Not only. We'll call about. We'll continue to talk about other families of modern operating systems after a break. So can you tell me, please? We have yet another session today, right? When does it nominally start?
At 5:20. So
5:20. So let's make a short break, maybe not 2 minutes, a little bit more. We'll start approximately at 5:40, maybe. Okay. So a break now.
Okay.
And then we'll start, and we'll still aim at finishing in time. Okay. Thank you for the moment. I'm switching off, letting my computer to record the session, and then we continue. Thank you.
Thank you.